First of all, I would like to thank the organizers for organizing this event for young mathematicians and also for inviting me to speak here. So basically, for this presentation, I will try to talk about some of my results during my PhD research with my PhD advisor Vlad Popescu about neural networks. Uh, first thing, first thing I will try to explain during this presentation some of the open questions in modern machine learning, and then I'll also try to present where we have managed to find some answers for these questions. Basically, I will try to give an answer to the following four questions. The first one is, in which conditions can a neural network interpolate a data set, or how people in machine learning call it, in which situation can it do you have overfitting? How many solutions do you have for this interpolation? Is it finite or infinite? Then we'll also give a description of the Hessian eigenspectrum evaluated at global minima point. And after that, we'll also give we'll try also to give a practical way of finding this point. Now, before diving into these issues, I will try to present what's the machine learning problem. So any machine learning task usually starts with a data set, let's say xi, yi, where xi represents the input data and yi are let's say the labels. So for example, if you have a task of image recognition, xi are the pixels, the matrix of pixels of the image, and yi is, for example, if it's an image recognition problem of detecting if in a picture you have a dog or a cat, then yi can only take two values. And basically, you want to find a function f such that yi is equal to f of xi, or at least yi to be approximately f of xi. Now, usually, when you try to search for this function, you search it in a family of functions that are parameterized over some parameter, and finding a good function that predicts your data means that first of all you need to define some metric between your prediction and, let's say, the reality. So you define a loss function, let's say called L, which measures how far is f of x, which is your prediction, from y, which is let's say the reality. So basically, you want to find a good theta such that this distance between your prediction and reality is as small as possible. So basically, you're trying to minimize the expected value of this loss function with respect to the distribution mu, where mu is the distribution after the data set is sampled. Now, in practice, you don't have access to this distribution. I mean, your input is the data set. So which means you cannot, let's say, compute in a direct way this expected value, but from the law of large numbers, you can approximate this expected value with its empirical version. Okay, so now we have defined what's the machine learning problem. Now the second thing that needs to be defined is what's a neural network. And I thought that the best way to describe a neural network would be first using some images. So I gave here two examples. Example A is a simple neural network with no hidden layers, which is also called a perceptron. And example B is a more, let's say, complex one, which consists of two hidden layers. Now, what does this graph mean? Basically, in example A, you have your data input, which has n. So you have one data point which has n coordinates, and you apply a linear transformation given by these weights W1, W2, Wn, and after that you apply a nonlinear activation function. Then basically that's a perceptron. Example B, it's the same procedure. In the first hidden layer, in each node, you compute a linear transformation from your input data, and then you apply a nonlinear activation function f, and you do that for each node from the first hidden layer. And then for the second hidden layer, the same procedure. You take the first hidden layer, you apply a linear transformation, and then apply a nonlinear activation function for each node. And the same goes for the output layer. Now, if you want to write this in a more compact way, you can write it in a matrix form as in this way. So basically, as I said earlier, you apply a linear transformation, then you apply sigma, then you apply another linear transformation, then again sigma, and so on. Basically, this describes a neural network with L layers. And here, just to make things more precise, when you say that you apply sigma to a vector, we mean that you apply sigma to each entry of the vector. Okay, now one important topic from, let's say, where my research starts is the double descent curve. Now, in the classical machine learning setting, when you want to train a model, you want to choose the right amount of capacity of your class of functions such that you don't get into underfitting or in an overfitting situation. Now, just to explain a little bit, by capacity, I mean, so capacity can mean, let's say, so increasing the capacity can mean increasing the number of parameters of your model, or for, let's say, for a neural network, it can also mean increasing the number of layers. And underfitting is the situation when you train a model on your training data and you get pretty low accuracy, and of course you get pretty low accuracy on new data. And overfitting is the situation when you train your model on a training data, you get pretty good accuracy, but you get bad accuracy on new data. So these two situations, you want to avoid them. And in the classical setting, the best image that describes this is this image A, where, as you can see, as you increase the capacity of the training, the capacity of your class of functions, this dot line represents the training risk, which decreases and starts to approach to zero. And then you have how the error evolves on new data, which has this U-shaped curve. So the best capacity is to choose somewhere here where it's the dot line. Now, in modern machine learning models, for example, over parameterized neural networks, this plot of the training risk and testing risk, it changes in the sense of that if you increase more the capacity of your class of functions, then you have this image B where again the training error, of course, it decreases, but for the testing you have this U-shaped curve, and then if you go, let's say, even beyond, it starts to decrease. So basically this tells us that if you increase very much the capacity of your class of functions, then your model will be it will be able to learn new data or even memorize it. Now, the main topic that I've tried to answer here is I've studied more the problem of interpolation. So I've been more interested in which situations can a neural network interpolate your data set. And before diving into these results, I would like to first state a result from an article of Alan Pincus. This result states that if you consider the set of shallow neural networks, so this set can be written as the span of these elements, sigma wx minus b. This set is dense in the space of continuous functions if and only if sigma is continuous and not a polynomial function. Now, why is this result important? Well, first of all, this has a direct consequence, which is the fact that if you have an activation function which is continuous and not a polynomial function, then you can achieve interpolation. Now, one of our original results is the generalization of this consequence for activation functions which are locally integrable and not polynomials. So basically, we have the following result. If you have a data set with xi, yi, and xi are distinct, if you assume the activation function is locally integrable and not a polynomial function of degree less than d minus 2 almost everywhere, then in the family of feed-forward neural networks with L hidden layers and the last one having a width of at least d, you can achieve interpolation. And basically this gives us an answer for the first question. Basically, for example, if we just think of a shallow neural network, you just need that the hidden layer to have at least d data points, where d is the number is the number of data points. We have also studied what happens if you assume that sigma is in general a polynomial, and and we have achieved some interpolation results. So basically, if sigma is a polynomial of degree m, and if you're in situation 1 where the number of data points is bigger than this quantity, then the interpolation problem from the previous proposition is not possible. But instead, if you have the reverse inequality and you also add the fact that this vector 1 xi tensor 2 times xi tensored m times are linearly independent, then the interpolation problem it is possible. Okay, so now basically we've answered the questions in which situation can we have interpolation or overfitting. Now the question is, do we have only one interpolation point? Are there a finite number of them or an infinite number of them? And this answer is given by a result of an article by Cooper, which says the following: if you have, let's say, a model described by some function f of theta, and the loss function is the mean squared loss function, then the set of global minima, so basically the pre-image of this function at 0, is generically, which means possibly after a small change of the data set, a smooth n minus d dimensional submanifold, possibly empty of R2dn. Now, applying this with our interpolation results to this theorem, which basically tells us that it tells us that not just that you have one interpolation point, you have infinitely many interpolation points, and this set of interpolation points has a manifold structure. More precisely, it is an n minus d dimensional submanifold. Now, just a quick remark: this result remains also true if because here the result is stated for activation functions which are smooth and not polynomials of degree less than d minus 2. But this result remains true if we change the statement with the statement of proposition of the statement with proposition 2, which was referring to the polynomial situation case. Okay, now the third topic was regarding the Hessian evaluated at the global minima of the loss function. Without diving into too much details, the result is the following. The number of eigenvalues of the Hessian evaluated at the global minima has d positive eigenvalues and n minus d eigenvalues equal to 0. This is true for shallow neural networks, and of course the number of hidden layers must be at least d.
Hi, Vlad. Sorry for the interruption. I just want to let you know that you have roughly 2 to 5 minutes left. So could you maybe
Sure. Okay, and the last topic is how you find such a point. Basically, this is let's say a probabilistic algorithm, which consists of the following. You initialize randomly the input to hidden layers, and sorry. Yeah, so you initialize the input to hidden layers randomly, and wait, just sorry, I need just to put my charger. It will be quick. Sorry. Sorry for that. So basically, the method is you want to initialize the input to hidden layers randomly, and then you want to optimize over V. So basically, your problem is reduced to a simple regression problem, and you will have also interpolation of your regression problem when this matrix sigma x of W transpose is sorry, and you'll have and also you'll have so basically the question is, sorry, so you want this matrix, and when this matrix has full rank, you will achieve interpolation. So basically the question is, how much over parameterization do you need for your shallow neural network in order to achieve interpolation? And this basically is given by this result, which states that if you have a shallow neural networks with which is described in this way, where W is initialized with independent normal variables, and if sigma is continuous and in L2, then if you consider the number of hidden nodes to be at least this quantity, which quantity is of magnitude d log d, then you will achieve this matrix sigma x of W transpose will have full rank, and it will have a full rank with a high probability, and thus you will achieve interpolation. Now, I just want to mention some of the future research directions. The first one is regarding the interpolation property for deep neural networks. So basically, it is interesting to study what happens if you decrease the number of decrease the number of width and increase the number of layers. See what happens. And the second thing, which is a more complex problem, is to study the double descent curve phenomena. Yeah, and that's all. Thank you for listening, and I'm happy to answer any of your questions.
Many thanks, Vlad, for the nice talk. So any questions for the speaker? There's a question in the chat. Is this double descent phenomenon mainly working in a concept of a sample size being extremely large?
If it's working in the situation
with a large data set, with a massive data set.
Yeah, I mean, these results have been so until now this has been studied in a more empirical way. So that's what let's say now mathematicians are trying to answer it. But yes, it can work on. I mean, most probably it can go wrong mainly if maybe the data set has a small size more. But if it's extremely large, then yeah, it should work.
Maybe let me ask another question. So instead of considering the feed-forward neural network, have you considered like more complex neural network structures like transformer, which is very popular nowadays? Have you considered study these?
No, I mean, transformers are already more, let's say, complex. I mean, also describing them mathematically. I mean, we still, I mean, the next more natural step would be to first understand for deep neural networks, if you decrease, let's say, consider a less number of widths on each layer, but you consider more layers. And maybe after we give a question to that, then yeah, maybe transformers will be the next step. Yeah.